Welcome again, guys. We're going to continue working with probability tree diagrams in this video. This time what's going to be different is that we're going to work with problems involving repeated events where there is no replacement. So you draw a card, you don't put it back on the deck, and then you draw another card, for instance. And we're also going to include conditional probabilities in this video. And so you're going to have to remember the formula that we learned previously, that the probability of an event A occurring given that event B has occurred is equal to the probability that both A and B occur divided by the probability that B occurs. We're going to use this formula a couple times within the video and use it anytime that you're working with conditional probabilities. Alright, well, let's get on to a card question first. This will be exactly the example I alluded to a moment ago. We're going to say that a card is chosen at random from a standard deck, and then without replacement, that's always a key term there, a second card is chosen. And we're going to first find the probability that both cards are numbered. Okay, so always pay attention to whether there's with replacement or without replacement anytime there's a repeated event that's occurring. We need to start by drawing our tree diagram, and we need to determine what the probability is that you would get a numbered card on the first card and then a numbered card on the second card. Now let me go ahead and draw the branches that we're going to use, and I'll show you how to fill in the probabilities later on, because you might not know how many numbered cards are in a deck. First, we're looking at just, do we get a numbered card or do we not get a numbered card? So again, we're working with a tree diagram where there's only two outcomes on this branch. And since we're still looking at whether we get a numbered card the second time, then we're just going to have two more branches extending from each one of those. Our next tree diagram will not look like this, although most of them that you work with do look like this. It just depends on how many possible outcomes that there are that you care about. Alright, now in terms of numbered cards, let's just list this out. The numbered cards would be a deuce, a tray, a four. Whoops, my screen isn't cooperating with me. Alright, 5, 6, 7, 8, 9, and 10. And then you've got, well, let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you've got 4 suits of 2 through 10s, don't you? So that's 36 cards in total out of 52 that are numbered. Now, I'm not going to simplify that in this case, and I think you'll see why in a moment. 36 out of 52 cards are numbered, which would mean the remaining 16 out of 52 are not numbered. Now, here's where the without replacement takes effect. Whenever we had 52 cards on the first draw and we took one but we didn't put it back, that leaves us with only 51 cards the second time, doesn't it? Alright, now let's suppose that we do get a numbered card the first time. There were 36 numbered cards. That would mean that there's only 35 remaining. And since there would only be 51 cards remaining on the second draw, you'd have a 35 to 51 chance of getting a numbered card the second time. Alright, and now as far as not numbered, well, we would still have the remaining 16 cards not numbered if we got a numbered card the first time, right? So 16 out of the remaining 51 would not be numbered. Okay, now what if we didn't get a numbered card the first time? And then what's the probability that we do get a numbered card the second time? Well, you would still have all 36 remaining numbered cards there out of the 51 cards that remain. But now you would only have 15 cards out of the remaining 51 that are not numbered. Alright, these two probabilities have to add up to 1, these two probabilities have to add up to 1, these two probabilities have to add up to 1. Every set of branches that you have, the probabilities have to add up to 1. Okay, now let's find the probabilities of the 4 outcomes in our sample space. You remember you multiply the probabilities along a path in order to find out what the probability of that outcome is. So we're going to have to first start with multiplying 36 over 52 times 35 over 51. And that will tell us that 1,260 out of the possible 2,652 combinations of 2 cards we get would be both numbered cards. Alright, and then do the same thing for the other branches. Do 36 times 16 over 52 times 51. You already know what 52 times 51 is, so just do 36 times 16, really. And so forth, on down the line. And you'll find that these, then, are the probabilities of each individual outcome. Now, we wanted to find the probability that both cards are numbered. We had actually already kind of done that, but I wanted to emphasize again that you want to make sure that all these probabilities add up to 1, meaning these numerators would have to add up to be 2,652. Alright, this is the only outcome in which both cards are numbered. Use your calculator to simplify that fraction. And you'll find that there's a 105 out of 221 chance that both cards would be numbered if you draw 2 cards without replacing the first one from a standard deck. Alright, another standard deck question. This time we're changing the outcome that we're looking for, though. I'm going to say this time we want to find the probability that both cards are diamonds. Alright, both cards are diamonds given at least one is going to be a diamond. Now, we're going to be using conditional probability here, and your clue to conditional probability is almost always that you see the word given within the statement that you're trying to find the probability for. Alright, so the probability that both cards are diamonds given at least one card is a diamond. Well, let's draw a tree diagram first of all for the situation that we're looking at. In this case, we only care about whether we get a diamond or not. It's going to be another 4-outcome tree diagram like you're used to seeing. Where on the first card we only care, do you get a diamond or not? And same thing on the second card. Do you get a diamond or do you not get a diamond? Alright, now you know that 1/4 of the cards in a deck are diamonds. And if you want to, for the first card, you can use 1/4 as your probability that you're getting a diamond, and then 3/4 is the probability that you're not getting a diamond. But on the second draw, keep in mind that there were actually 52 cards, and if you got a diamond the first time, and there were 13 diamonds, now you only have 12 out of 51 remaining cards that are diamonds. Does that make sense? Now, you might have preferred to put 13 out of 52 right there to make this a little more obvious. Up to you which way you want to go with that. And if 12 of the cards are diamonds out of 51, that means the remaining 39 would not be diamonds. And then let's say that we did not draw a diamond the first time, so you'd still have all 13 diamonds in the deck. What would be the probability that you do get a diamond the next time? It would be 13 out of 51. And now you would only have 38 non-diamonds remaining out of the remaining 51 cards. There you go. Now we're going to fill in the probabilities of each outcome. And then I'll show you how to find the conditional probability that we're looking for. Now you need to pay special attention to the words that I use here. I'm going to write down a lot of symbols, but the words are going to be very important. We want to find the probability that both cards are diamonds, right? And here's the way I'm going to label it. I'm going to say, let's find the probability that we get a diamond on the first draw and a diamond on the second draw. And we want to do that given that we get at least one diamond. So given that we get either a diamond on the first draw, or, remember the union symbol is for or, that we get a diamond on the second draw. And so the way that we're going to calculate that probability is this. Remember, you want to find for conditional probabilities the probability of both events occurring, both the one that you're looking for and the one that you know will occur. So we want to find the probability that we get a diamond the first time, a diamond the second time, and we either get a diamond the first time or the second time. That looks complicated, it won't be so bad. And we want to divide that by the probability of the event we know is going to occur. We want to divide that by the probability that we get a diamond the first time, or we get a diamond the second time. Okay, again, the words are most important there because that symbolism, especially up here, looks kind of complicated, doesn't it? Okay, So what's the probability that we get a diamond the first time, a diamond the second time, and we get at least one diamond? Well, if we got a diamond the first time and the second time, we got at least one diamond, didn't we? There's only one outcome that's going to fit that. Now I'm going to use different colored highlighters to show you where I'm getting these different things. The only outcome where you get a diamond the first time and a diamond the second time, and you get at least one diamond, is that outcome right there. That's 1204. That's going to match up with this. That's how I'm color coding. And then we want to divide that by the probability that we get at least one diamond. Well, so let's say we use purple here. Where are the outcomes where you get at least one diamond? Well, all right, that's going to match up with this, by the way. You get at least one diamond if you got two diamonds. You got at least one diamond if you got a diamond the first time but not the second time. And you got at least one diamond if you didn't get a diamond the first time but you did get a diamond the second time. The only outcome where you did not get a diamond is the last one, correct? Okay, so watch what I'll do with this then. The probability of getting both diamonds was 12 out of 204. The probability of getting at least one diamond was the sum of these three outcomes. 12 plus 39 is 51. 51 plus 39 is 80. It was 80 out of 204. All right, and then so the overall probability would be 12 out of 80. All right, because you've seen this enough time with conditional probabilities. These denominators are the same. They'll end up canceling one another. 12 out of 80, which of course then is 3 out of 20. All right, let's look at a non-card example. This time we're going to say that 3 discs are drawn. So we're not just having 2 events, we're having 3 events. 3 discs are drawn at random, in succession, and without replacements, from a bag that contains 5 blue, 3 yellow, and 2 red discs. What is the probability that you obtain 3 discs of the same color? All right, our tree diagram is going to look different this time because of 2 things. There are 3 discs that we're drawing, and there are 3 different possible outcomes for what each of those discs can be. This is going to look like a really big tree diagram because it is kind of a big tree diagram. For the first disc, you can have blue, yellow, or red, correct? Then for the second disc, same thing, and the third disc, the same thing. Now I'm going to pause and talk about this here because I want to show you how we're going to make a smaller diagram, because we've already hit 9 branches on the second disc. We're going to end up with 27 branches on the third disc if we continue this way, and it's a valid way of doing it. But look at what we care about. We care about whether we obtain 3 discs of the same color. So once we get a blue disc, all we care about is do we get a blue or not a blue the second time. So I can actually just make it so that there's 2 outcomes on the second draw and 2 outcomes on the third draw, honestly. See how that's working for the second disc? If we got a blue the first time, did we get a blue or not the second time? If we got a yellow the first time, did we get a yellow or not the second time? And so forth. Now, for 2 reasons, I'm going to go ahead and not label every single probability that you can get. First of all, it's a huge diagram, right? Second of all, you kind of seen how this is done already. So as long as we can focus on the outcomes that we care about, then we can go ahead and lessen the work that we're about to do here. We want to know the probability that we obtain discs that are all the same color. And so there's only 3 outcomes that we care about. We care about, did we get 3 blues? All right, so this path. Did we get 3 yellows? This path. Or did we get 3 reds? This path right here. Those 3 paths are the only ones that matter to us. All right, now let's find out what the probability of each is along the way. There were 5 blue, 3 yellow, and 2 red discs. So that means there were 10 discs in total, right? And so you had a 5 in 10 chance, obviously, of getting blue the first time, and so forth. Now let's travel this top path here. And again, we only care about the paths that I highlighted. If we got a blue the first time, that would mean there's only 4 blues the next time, correct? And there would only be 9 discs the second time. So you would have a 4 in 9 chance of getting blue there. And then if we continue that, on the third disc, there would only be 3 remaining blue and only 8 discs remaining total. So you'd have a 3 out of 8 chance of getting 3 blues, or the blue the third time in that situation. Which means that the probability of getting blue 3 times would be 5/10 times 4/9 times 3/8, which is 60 out of 720. All right, then using similar logic, we could say that if we got yellow the first time, there would only be 2 yellow discs remaining for the second draw and 9 discs remaining. And then if we got a yellow the first time and the second time, there would only be 1 yellow disc remaining out of the final 8. So you'd have a 1 in 8 chance there, which makes the probability of getting a yellow all 3 times equal to 3/10 times 2/9 times 1/8, or 6 out of 720. And then finally for the reds, well, this one turns out to be super easy. There's only 1 red out of 9 if you got a red the first time. And then if you got a red the first 2 times, there aren't any more reds remaining, are there? Of those 8 discs. So it turns out you've got a 0 out of 720 chance of getting all 3 reds. Now the probability of getting all the same color then would be the sum of the probabilities of those outcomes. That's 66 out of 720, which is 11 out of 120. Alright, now you've seen how to use tree diagrams when replacement is not involved. I did have another example there, but again, we're kind of pushing the time limit that I want to use for this video, so let's go ahead and stop it there, and we'll have more examples in class. Thanks for your attention as always, guys. Good luck with these questions. See ya.